No,
Okay. Well, then let's start, and I would first of all like to thank the organizers, not just for giving me the opportunity to present some work here, but also for inviting me to stay for a longer period here at the Newton Institute. So I was asked to deliver a kind of introductory presentation on numerical methods for solving quasi-variational or variational inequality problems. And I think I should start with the kind of disclaimer up front. So this is a broad topic. I will not be able to cover everything. In particular, there might be many colleagues of mine who will be disappointed by not mentioning their particular method for solving the problem. So I'll give you a perspective which is related, I would say, to research we did over the past couple of years. It's in particular related to generalized Newton methods. This is one of our underlying theme here. And I also would like, of course, to acknowledge that there was support from many funding organizations, as you can see here on this list of icons. The left one is just my alma mater, the Humboldt University. The other one is the Mathian Research Center, which is a huge DFG research center, which is going to end as a DFG center by the end of May, but is going to continue within the Einstein Center of Mathematics in Berlin. And there's the Berlin Mathematical School, which is a graduate school for PhD, but also diploma students. Then, by the end of last year, there's this START project, which was still anchored at the University of Graz in Austria, where I've been some time ago. So it finished last December, and it was, after all, then it turned out 8-year project on interfaces, free boundaries, and related projects. And this was funded by the Austrian Science Fund. Okay, and of course there are many collaborators. You may see some names as I go along, but otherwise, somebody's interested, I have a list of papers, and then you get all the names, and I can show you pictures, and then you also get all the faces. Okay, so let me start. So I would like to start by looking at a certain general form of a variational inequality, as you can see it here. So we are looking for a function or an object, little y, in some space, capital Y, such that this relation here is satisfied for all elements V in this space, capital Y. Well, what are the various objects here? Capital Y is a Hilbert space for the time being, Y star. Whenever you see a star, which hasn't occurred so far, well, it does actually here, it's the topological dual space. I denote duality domains by these angles here. I try to be consistent already, I should mention this here with the notation throughout, but don't be too harsh on me if I jump out of the notational context at some point in time. And please ask and interrupt whenever something like this happens or questions emerge. So little a is supposed to be a continuous, coercive, bilinear form. The coercivity constant, which will show up in some of the estimates later on, is denoted most of the time by little u, and of course is supposed to be positive. And there is a function phi from y into the extended reals. This is where you see this little bar on top of the r here. This is supposed to be a proper convex function. Well, proper function is a convex function is a function which is has a point where it's finite, so it cannot be all over plus infinity, and it should not have a point where it should not be identically minus infinity. This would be a proper convex function. And f is supposed to be in y star in this dual space here. Okay, so this is a general format, and according to the specific definition of this little phi here, there is usually in the community a distinction between what we call a variational inequality of the first kind and a variational inequality of the second kind. A variational inequality of the first kind would be an obstacle type problem. So this is, I would say, maybe the most famous example. You have this membrane which probably is clamped on the sides of some some domain. And then there's a force pushing on this membrane and pushing the membrane towards an obstacle, and partially the membrane will touch the obstacle and partially it will not. And in this particular case, this function phi is identical to an indicator function of some set k. I mean, in the obstacle case, it could be just some simple constraint set of the form. I'm probably too detailed here, but just let me know if it gets boring. The computer already thinks so, but you know what happens. So automatically turns off.
That's okay.
Okay, so we have a k in this case would be y less equal or greater equal some psi in the domain. Omega could also be just partially on the domain. So this would be a particular example for this set K here. Of course, it will be, there are other examples and I'll tell you some later. Well, obstacle problems very often are considered as sort of simpler models for contact problems, where you then move typically into 3D and you have contact on the boundary rather within the domain. You could also come up with so-called non-penetration condition for crack problems. So if you have a material and there's a crack inside and you have forces acting on the material, then the faces of the crack may get into, may touch or just detach in certain regions. And this would be another variational inequality of the first kind. Whenever the function phi is not just an indicator function, but, and I should also say that throughout we assume that the set K is a convex set, because otherwise the problem is getting kind of very complicated. So whenever this little phi here is not an indicator of a convex set, but it's just a proper convex function, then we would call this object, which we've seen on the first slide, a variational inequality of the second kind. Specific examples would be simplified friction problems. I will come back to this later on. You will see that there's a very simple choice of phi. Bingham fluids are specific examples. If you volunteer, you see sort of a little sketch of what the Bingham fluids occasionally does. If you would like to seal an oil well, for instance, in drilling, then you would have concrete which goes into this well, and this should somehow close it, and this would be a specific example of Bingham fluids. There are other liquids, of course. There could be Bingham fluids. For instance, yesterday night's ketchup, I think, behaved almost like a Bingham fluid, at least when I ate the burger. Then there is total variation regularization, which is an image restoration, a kind of famous regularization tool or technique. Well, I don't want to go into the details, but just very briefly, what you're interested in this application is where you're given noisy, possibly also blurry image data, and you would like to reconstruct the original image as good as possible. And then, of course, this is usually known to be an ill-posed problem because of some blurring operation which may destroy information. On top of that, you have noise. And in order to get rid of noise, you have to regularize, filter. And total variation has the advantage, as we know, that it allows jumps across n-1 dimensional manifolds, which, for instance, certain Sobolev space functions would not admit. And this is an advantage because a jump in a function would be considered an edge in an image. So if you would like to preserve...
Why is it a variational inequality? I thought it was a minimization problem.
Well, it is, because variational inequalities...
Yeah, but why variational inequality in the image restoration?
Well, because the first order condition of the problem... So I can write down the problem.
Sorry, which function gives
the first order condition?
I want to recall.
So you would do the following. So you're given image data, let's call this data Z. And the data usually is in L2, omega is our image domain. And what you would like to do, you would like to track the data. You would like to find a U, which should be the reconstructed image. Let's assume there is some blurring on top of the U, which makes it less sharp. So this is a known operator K. There's another problem where this is unknown. And then we have to filter. Even without this, when K would be identity, we would call it the denoising problem. We do not like to minimize this right away because it means U would be equal Z, depending of course on the space, but let's assume it's large enough. U could be equal Z and Z could be noisy data, which we don't like. And so we filter. And this would be the total variation here. So the usual definition, I think I don't need to write it down, it's the supremum in this dual form, and alpha is a positive parameter, which does the following. If alpha is very large,
is total variation.
and this is total, so this is total variation.
Okay.
And this acts as a filter now, because it requires me that I have to leave the space L2, I have to be more regular. So now I'm looking for functions
VV.
In PV of omega, so this is more regular than L2, but because I'm in PV, and this is why usually, I mean, you may also wonder why I don't use something like this, for instance. would be much more convenient, it's differentiable,
Yeah.
everything is fine, but then the trouble is I would not admit jumps because of the regularity occurring from
You don't recover the lines.
Okay, and now if you're so now we need to characterize first order optimality. This is a convex functional, and first order optimality would give rise to a variational inequality if you wish. If you minimize.
But it will give rise to the Euler-Lagrange equation.
Yes, but it's not an equation.
Not
Because-
differentiable.
Because this term is
Short-
not differentiable.
Short answer is non-differentiable functional.
So this is a convex. So this is a convex but non-differentiable function
So this is why you get operational inequality,
of the second kind. Yes.
not of the obstacle type.
Not of the obstacle type. And if you write down the convex inequality, then you, I mean, so
Yeah, I was misled by
Yeah,
this
no, it's
idea
fine.
that in the old times variational inequalities was most of times the first type. So
Yes.
this is the second
This
type.
would be a second type, a second kind. Yes. Was another question?
So this DV that you consider, it's just that because I mean people in image processing, they just saw that the picture at the end is what one considers the better picture,
Yeah.
or there is a fundamental. I mean, image is what? I mean, it's the high wavelength limit of Maxwell equations. I mean, this is how it's created. I mean, is there some fundamental analysis that at the end this is the right thing from this physics point of view, or?
No, I think there are two aspects here. I mean, so this aspect is I have an image. I mean, I'll let you just
go there.
They just want to preserve contours.
You
See
answer
the
later,
lines.
maybe.
Yeah, I could answer it later,
Is
but let me
there a
just.
derivation
Okay.
of it that
So
is?
let's assume.
No.
So let's assume the following. I'm just
Answer
giving an
later.
image.
This is a big deal.
So I'm just giving an image. So this could be this little zebra image here. So here, of course, we could think about the physics. It's a little camera with how many megapixels, but I'm not necessarily talking about magnetic resonance images or
So,
computer to
but
mass.
I want to say that people took this and they saw that it's, if
No,
they
no.
minimize it,
No,
it's,
no. Yeah, yes,
then
but
it's
the point is
very good
analysis. Well, as I said earlier, you could say, well, if I would like to denoise, I minimize the least squares distance. But then you would pick up the noise, because that is noisy image, as you have just seen. So you would like to filter out noise. Now, one way to filter is to add a regularization term. So this is a principle which is, well, very often used in English problems. Okay, and then you add a filter term. Now you may say, I add a filter term like this because it's more convenient, it's differentiable, but then your function u is quite regular. And if it's quite regular, well, then you have to have a sort of a priori decision to say, well, do I need a function which admits jumps? Because a
So
jump
exactly,
relates
the
to-
judgment is done just by aesthetics, that's it.
Well, this is another question, but I think at some point I have to stop you because the difficult, no, because I mean that's one of the fundamental difficulties to judge what's the good quality of a
But I think
reconstruction.
that you can say one word that explains more or less, which is you lose contrast.
You lose
Contrast
contrast,
is very important for people.
Contrast is important. I mean, each filter will somehow have an effect.
So BV preserves contrast.
Not really,
So why do you do that?
but it preserves edges.
Oh, edges.
So this one doesn't preserve contrast, and it does also not preserve edges. So this one has an effect on the contrast, but it preserves edges. And so it's a sort of a priori choice what you would like to see.
So
So it's
you
a
want
kind of
these
modeling
edges.
question.
You want to preserve edges.
You want to preserve edges, take out the variation. And the answer here would be, well, there are many measures. So one measure is peak signal to noise ratios. Or there are certain structural similarity measures. This is how people try to have a kind of automatized quantitative rule to judge the quality of an image. But very often, of course, it boils down to eyeball norms and what people would like to see. For instance, medical doctors are usually not used to see total variation regularized images. Because there is another effect, but I think then I leave the topic here. The other effect is that you get a reconstruction which has the tendency to be piecewise constant. So this is the effect of total variation. So in 2D you get this sort of blockiness. Now if you transfer it to human tissue, your tissue would not have a sort of soft transition from one, say, gray level to the next, but it would always be in jumps, so sort of quantization. And this is something which is not usually convenient for diagnosis purposes. And then you do some local regularization. I mean, so this is a huge field in its own right. So I think I could give another talk, I think, on image processing.
Sorry, interrupt.
No, it's perfectly fine. I'm happy to talk about these things. It's a huge topic. I think if there's interest, I'm happy to continue. Okay, so now let me quickly go back. I was at the beginning. Okay. All right. So now we have discussed the variational inequality of the second kind, and I think it's well clear that there is a convex function added probably to some objective, but of course we know that variational inequalities could arise in their own right without being first-order optimality conditions of minimization problems. Okay, so what are my goals here? I would like to stick to function spaces. Although I'm giving you a talk on numerical methods, I still would like to stick to function spaces. So I would like to define a very abstract framework which works in some Hilbert or Banach space. I'll give you a reason why I'll do so, and the major reason is mesh independence of the corresponding method. It should have fast local convergence. This is why I usually look at Newton-type schemes rather than project a gradient or other type of methods. It should be generally applicable to both types of problem classes, and I prepared another little presentation for the afternoon. If it comes to that point, we will see also quasi-variational inequalities of elliptic type at least. And ultimately, I would like to intertwine the numerical solver upon discretization with adaptive discretization. So we should somehow adaptively find regions where you should have a better resolution or a finer triangulation as compared to regions of the domain where this is not so much necessary. This would, of course, reduce the number of degrees of freedom. And then there are many speed-ups which I won't address here. Multi-grid solvers for solving linear systems. Some people try to approach the problem by kind of multi-grid of nonlinear type. These would be details and aspects I cannot cover here. Okay, so let me go back to variational inequalities of the first kind, and I'll try to explain the basic concept of the solver, the basic difficulties, and the reasons why we approach the problems the way we do. Okay, so let's assume we're given the following. So we have an obstacle psi, which is positive on the boundary, or at least non-negative, which is sufficiently smooth. We have a force in L2, could be h minus 1, but for some reason I would like to have it in L2. For the time being, omega is a bounded domain with a certain regular boundary. It should be Lipschitz here. Y is taken here to be h01. And I consider what I have written down before. I have this constraint set k. I'm looking for functions in h01 which are not larger than the given obstacle in the almost everywhere sense. Okay. Well, then we know, of course, that there is a minimization principle. If you write down, for instance, the obstacle type problem, we are minimizing a quadratic energy subject to a constraint. And then we would get the sort of first order condition, and I realize if I write here h2 I need a bit more than Lipschitz in this context here in general. But let's assume that the boundary is sufficiently regular so that the solution is not just in h01 but in h2. Well, we know that for the obstacle problem the minimum regularity would be h01, then giving rise to a Lagrangian multiplier lambda here, which would be in h minus 1. But for the next explanation, I would like to have this a little bit more regular. So this would be an object now in L2, and what you see here is another form of writing a variational inequality. I mean, maybe I should have at least written down the variational inequality once, which arises here. So if you minimize a quadratic energy, but if you are minimizing 1/2 ay, comma y in this duality pairing, and here we have the L2 product subject to y less equal psi, well, then you get the usual variational inequality for this. So the first order condition would be, of course, we have, let's assume A is symmetric, so we have A, y, and we have minus y, equals 0 for all v in this set K, which is as I defined it above. And of course, y has to satisfy also the constraint. So this is one way of looking at it, but the other way, I missed the F, sorry. So I should have at least written down F of E, all V and K, and Y should also be an element of K. Okay, so this is what we would see as a variational inequality, but from certain perspectives, it might be also convenient to add or to bring in a slack variable or Lagrangian multiplier. And this is what you have
How
seen.
to say V minus Y next to the F?
Oh yeah, of course. Sorry. Could be V minus Y. Again, for all V in K. Yes, of course. Okay, and so one alternative way of looking at this, which is probably more an optimization kind of way of looking at this, is by introducing this Lagrangian multiplier lambda here. And under this additional regularity assumption, I can claim that lambda exists as a function in L2 of omega. In the minimum regularity case, it might just be H minus 1. In H minus 1, I don't have a way to rewrite the conditions here, because lambda, obviously, if I bring in a lambda down there, it has to have certain, has to satisfy certain conditions. One would be non-negativity. The other one would be, it should be complementary to y minus psi. Okay, I mean, if you're in the minimum regularity case, lambda star should be greater equal 0 in the sense of h minus 1, and it should be complementary to y star minus psi in the sense of the duality pairing between h minus 1 and h01, or h1 star and h1. But if I do have more regularity, then I can rephrase this complementarity relation, which you actually see down here in a pointwise fashion, as a non-smooth equality relation here. So this would be the usual conditions which I just discussed in the minimum regularity case. If you have more regularity, well then what was non-negativity in the sense of h minus 1 becomes non-negativity in the pointwise almost everywhere sense. So it's just in L2 the lambda star, and this can also be interpreted in a pointwise almost everywhere sense in this broad condition. And these three conditions usually go along with the first equation. Yeah? In order to and this looks complicated in a sense. We have two inequalities and one product condition. And this can be rewritten equivalently as one equation where the plus here denotes a pointwise max of 0 and whatever function is inside the parentheses here. So then this here is equivalent to that here. Okay. Well, the first observation is we were able to rewrite a variational inequality as a system of equalities. And now, of course, you may wonder, where is the inequality gone? Because inequality is a complicated phenomenon usually. Well, and it's somehow hidden in the fact that I had to add here the plus and have to use the max operator. Now you may say, well, that was a choice. There might be other functions giving me such relations. But it's a kind of inherent principle that whatever function you find, and there are many, you will always find a non-differentiability somewhere. So the inequalities here and these relations transform into a non-differentiability. So somehow, at least what I achieved is I rephrased a system of inequalities and equalities as a system of equalities only, and the price I pay is non-differentiability.
Which means non-differentiability is because otherwise you don't find the free boundary.
Yes, if you wish. So the free boundary is related to the non-differentiability. And usually I would say the free boundary is precisely where we hit the non-differentiability. So this is where the max is non-differentiable. So that's the observation. Okay, now of course if you have a system of equations, you may say, well, I would like to find a numerical solver which is efficient, and probably the first thing which comes to mind is Newton-type procedures. Okay, solving, because after all it's a nonlinear system, at least in the second part, so we use Newton. Trouble, of course, is now we have a non-differentiability, so we need to understand to what extent we are able to extend Newton-type solvers to the non-differentiable world. I mean, for the smooth world, Newton methods have been well used for a long time in finite dimensions for sure, and in infinite dimensions there are abstract papers using Newton's method in Banach spaces for smooth operator equations. But what we see here now is, if you wish, a simple example of a non-smooth operator equation in an infinite dimensional setting. Okay, so a direct application of a Newton scheme is questionable because of non-differentiability. Now you may say, well, but if you would like to do numerical solutions, by the end of the day we anyway have to discretize. So we discretize the problem. Well, that's what you could do. You discretize. There are finite dimensional generalized Newton schemes. You can apply those schemes, and the methods will converge for every finite dimensional instance. I mean, they converge usually locally at the fast rate, which would be superlinear or even faster because of the specific choice here, the max function. But then, and you could generalize those methods, globalize those methods by so-called path searches. But then the question is, if I keep on refining the meshes, because that's what we usually try to do in numerics, will I have this nice convergence behavior in a robust and stable way for all mesh sizes? And the answer in general is no. So what you will see, and I'll show you an example later on, is a mesh-dependent behavior of a simple finite dimensional Newton scheme. Okay. And so we would like to come up now with a solver which has a sort of infinite dimensional connotation and converges after discretization in a mesh-independent way. Okay. One way to do so, and again this is a choice, is probably our choice, is the following.
So,
Yeah.
so in this previous equation,
Yes.
the second, what you call the second equation,
This one.
you can replace y star by using the inverse operator for a, I guess. So it's a problem just for lambda.
Yes, you could reduce
That would be,
yes.
that's a fixed point equation for that.
Then it's a fixed point. Yeah, you could
And I
say
guess is the case that C is sufficiently small, it's a contraction.
yeah, yeah,
So that's one way you could try to solve it by fixed point
that is
iteration.
true. So I mean, there are other solvers, and I'm sure you can.
No, I'm not saying that's a good method.
No, it's fine. So the point is, I agree. So the C here, which I haven't mentioned so far, is just your choice. It just needs to be positive because of inequalities sitting down there. And there might be choices of C and a reshaping of these equations so that you get the contraction, and then you have convergence, but this would be at best sort of linear type convergence. And usually it could be quite slow.
The problem is this it's a fixed point equation for an operator which is Lipschitz, but it's not differentiable.
It's not
This is the big issue.
Let me ask you,
Yeah.
what is the advantage of writing lambda star? Because you already know what lambda star is.
But not up front. So in what sense do you mean? Well, I have to ask
Well,
first. but
Well, lambda star to me is, of course, the A of psi when they touch.
yes. But
And there's a measure which is positive,
yes.
is exactly on the,
Yes.
and so what you're writing is basically lambda star is F minus A of Y star.
Yeah, but the point now would be, the question is, where do they touch?
Yes, we
This
don't
is
know
something
that.
we do not know a priori. So, I mean, if somebody would give me the information, that is the coincidence set or the active set, then I would say fine. With this, I only have to solve a linear system, and I can solve the overall problem. But the difficulty is, I can view it from two ways. Either I say I have no information on y and lambda, and I have to solve the equation. Or if I have more structural information, and I agree what you're saying is correct, but then it involves the knowledge on where is coincidence and non-coincidence. Or
So it's a tracking device for finding.
Yes. This would be, so you may also say it's a sort of tracking device. And I mean, but something I don't cover here, I mean, in a different context, we precisely did this. So we said there are sets up front which we need to identify, and once I have the sets, the coincidence and active sets or guesses, then I can identify lambdas and y's as functions of those sets. And this then is a sort of shape optimization problem, but still I need to find those sets. I mean, either I need to find the sets, which then induce a lambda and y, or I find y and lambda, which then give me the sets and also the free boundary. So this is two ways of looking at the same problem.
I have
Okay.
a question, just one question.
Yeah.
Is this related to the method of penalization?
Not
Some
at
say
this
it's-
point.
Yeah.
Not at this point. At this point, I'm not penalizing because I'm only rewriting complementarity. So I write down a first order condition, no penalization.
It has a measure, so it's not very.
Yeah, but in some sense, the second equation could be rounded a bit and take it to
The next step.
Lots of anticipation on Charlie's side. Well, there are two ways. Well, one way is to say I'll round the max. I agree. Okay, this can be done. No problem. So I'll smooth it, and then I have a smooth system, and then I have a sort of alternatively, and this is what we usually do, is to say, well, we regularize the indicator function. So we had for variational inequalities of the first kind, we have the indicator function of this convex set, and we use the Moreau-Yoshida regularization of that indicator function. Well, this is a well-defined and well-understood object in its own right. Well, we know, although the original function is just convex and not necessarily differentiable, its Moreau-Yoshida regularization will be continuously differentiable with the Lipschitz continuous derivative. And there's a lot understood about the minimizers of the regularized and the unregularized functions and so on. In general, of course, it could be also complicated because the Moreau-Yoshida regularization is in its own right an infimization or minimization problem. And if the set K is complicated, we should not believe that we can get an explicit characterization of the indicator of this Moreau-Yoshida regularization. But if the set is simple enough, like in the case for the obstacle problem, you can get an explicit characterization of the Moreau-Yoshida regularization. This would be the corresponding term. So one way is to say I now look at still the constraint problem. But written in a different way. Okay, the constraints are now sitting here. So here I wrote them as explicit inequalities, and this is equivalent, of course, to adding the indicator. Because whenever I don't satisfy this constraint, I get the harsh penalty of plus infinity, and whenever I satisfy the constraints, well, then this is 0. Okay, so this is completely equivalent. Another point of view here would be to say I replace this by the Moreau-Yoshida regularization of this indicator function, and this is what you have seen here. So this is this term here. First of all, without the lambda bar. Okay? And if you allow what we call a generalized Moreau-Yoshida regularization, which is not just the classical one, but adds a term which involves a pre-given lambda bar, then you end up with this formulation.
Well, a priori estimate in your parameter gamma.
What do you mean by a priori estimate?
Your parameter gamma should go to 0, or how is it?
No, it should go to infinity.
Infinity, okay.
Yeah. Okay. So it's because there is something sitting in here. If you pull it out, then it should go to infinity. So now I may say, okay, with lambda bar equals 0, it looks like a standard quadratic penalty, and there's not an argument against this. With lambda bar not equal 0, it starts to look like an augmented Lagrangian type method. And if you consider lambda bar to be an estimate of your Lagrange multiplier lambda star, if it would be the true lambda star, then it's known that the finite gamma in the regular case may give you exact penalization. But of course, we usually don't know, and then you may have a sort of update scheme to this lambda bar. Okay. So this is now a sort of unconstrained form of this. Of this problem which I've written down here, where I have regularized the indicator function by Moreau-Yoshida. Now, if I write down the first order optimality condition, I end up with this problem here. So now I have one operator equation. Still, there's a non-differentiability. The question is, what's the gain? Okay, so what you can see here now, on the previous slide, I had a first order system where I had a non-smoothness. On this slide, I have a first order system which looks a bit more compact. Okay, that's nice. But on the other hand, it still involves a non-differentiability. So I have to inform you what's the gain. But there's a question.
So I just want to understand better this lambda bar. So
Yeah.
if the lambda bar is the correct Lagrange multiplier from beginning, then we have better rate of convergence when gamma goes to infinity.
Yes, the point is, in the augmented Lagrangian setting, and this is how I may look at this problem then, it is known if I have the correct guess here, then there's a finite gamma which has then for a finite gamma the solution of the original problem is a solution of this penalized problem for finite gamma. So this is what we call exact penalization. Without this lambda bar, it's the quadratic penalization, and this is known to be never exact unless the constraint is redundant, which means y automatically satisfies the constraint. So there is a gain by adding this lambda bar. At least theoretically and numerically one has to see, but certainly, usually we don't have the multiplier at hand up front. Okay. So, okay, now I have to explain why this is more convenient than what we had before, despite the fact that we still have a non-differentiability. Okay, well, first of all, I'll set up an algorithm. How could we solve this problem? And then I'll try to explain why it's good, and I'll be more detailed later on. Okay, so what could be a simple way? We could say we fix some lambda bar. Okay, let's get this complication out of our game here. We just fix it. In a different algorithm, we may even consider updating lambda bar, but this is something I would not like to do right at the beginning. We have an initial guess of y and some lambda 0. Well, there was not really a lambda 0 involved here, but if I go back to the first order system, I see that this equation somehow looks like that equation if I plug in this relation for lambda star. So if I take this green one, plug it in here, then the reduced system looks a little bit like this system, okay, except for the fact that I would need to see lambda star here, which I don't. I have a lambda bar, so I may consider this here a sort of regularization of the multiplier lambda star, and this is indeed what it is somehow. Okay, so this is why I keep denoting a lambda here in the algorithm, because ultimately I would like to find an approximation for this multiplier lambda star. Okay, so what I need to do is I need to understand the non-differentiability. So there was a max involved, and inside the max there was this expression here. Okay, so we make a distinction between wherever we are on the positive side of the max and the rest. So on the positive side, I call this an approximation of the coincidence or active set. This is why you see this calligraphic A here. And the opposite would be the inactive set, or a sort of guess of the inactive set. This is where this would be less or equal to 0. Okay. So this is now a way of bringing active and inactive set estimates into this with respect to the max operation and the non-differentiability of this max. Well, then I do the following, and here I again use this notation. I had an operator A, but the operator A uses a bilinear form. This is this little a here. And now I solve this equation here, where we almost see what we have seen before, except for the fact that the non-differentiability is gone, but there is a characteristic function of the active set. Okay, so multiply this object here by the characteristic function. Let's just look at this on the active set. Yes?
This is a bit like saying that you're computing derivative almost everywhere of lambda plus to get the heavy side.
Yes, indeed.
And you just plugged in the, yeah.
Yes. So, I'm bringing this up because inequality constraint and optimization have been treated by active set procedure. So you try to guess, well, that's what we discussed before, where is the coincidence set? Because then I have lots of knowledge on lambda and on everything, and I could solve the problem. But then the difficulty is how to find those sets, and this would be one way of estimating those sets. But there will be a different look if you come down there. I'll very soon try to convince you that this is a specific type of derivative of the max operation which is acting here, and there's a sort of equivalence between this active and inactive set procedure and a generalized Newton scheme where I have a specific generalized derivative of the max. But what I need to solve in this step here, this is a linear equation. There is no longer a nonlinearity in here because I have somehow removed the nonlinearity by bringing in this characteristic function of the active set. And if I'm interested, I mean, for solving the Mohoyo-Ishida regularized problem, I don't need to go through step 4, but if I would like to get an estimate of this lambda star, I would like to also compute this step 4. On the inactive set, of course, lambda is 0. This is the structural information we know up front usually. And on the active set, well, if we just for the time being would get the true solution y star on the true active set, and we would set here the lambda bar equal to the true lambda star, then this would be just the correct multiplier as you would need it for solving the original problem.
What does this the initial state you start with? What does it do with the actual solution? Does it want to compare it? Suppose you have the actual solution.
Yes.
And you choose a lambda.
Yeah.
And so what exactly is the next step in the sense of the picture of the coincidence set? So what happens next stage?
Well, I'm not sure whether I understand. So I do what? So I say
You start with a lambda.
some lambda.
Lambda bar.
Okay. Yeah.
And then that's basically, it's supposed to be the difference between f and the minus
Yes.
operator.
Yeah.
And so it is, now you're saying the set when it is strictly larger than positive.
Yeah, I mean, let's say one meaningful guess would be if let's assume the obstacle is smooth enough, take the max of f minus the operator applied to the obstacle. Because we know that whenever this object is negative, well, this is not where lambda could, this is not where we could have a coincidence. So I could bring in lots of a priori knowledge here, based on
I'm
the
trying
data.
to see what the picture is, I mean the evolution of.
But yeah, this is hard to judge for me because it also depends on the gamma. So what you could see, and it depends on the initial guess of y. So if you have, let's assume we bring in here the correct lambda star even, but I have a bad guess of y star, and I have a certain choice of gamma. Well, I get some sort of estimate, so I cannot particularly say that this would be close to the active set at the solution because it depends on the y. I mean, what's going to happen? I think there is there might be a certain monotonicity. It's like you have an overestimation of the active set, and then you shrink until you see the active set. But that depends on your initial guess, because you might not have an overestimation depending on your choice of y. Because y is completely arbitrary here. Again, we could think about, should it be feasible? Of course, it makes sense to choose y 0 less equal psi. But here it's completely free. So if you have a strange initial guess, it's a strange initial active set, and then you somehow have to move to the right active set. So I think good initial guesses, of course, may give you a very good active set.
But you have a uniqueness, right? It's the whole problem.
The problem is unique, yeah.
The particularity, yeah.
So I get, this is correct. I mean, each step here has a unique solution,
Okay.
but of course it depends on sort of pre-information, which is good or bad, and depending on the quality of that information, I have a good estimate of y star or not such a good estimate.
So if you do the procedure 1 to 4,
Yeah.
send k to infinity,
Yes.
then the theorem is that this algorithm converges.
Yes.
And what it converges to is a solution of the Moreau-Yasuda regularization. It's not a solution of the obstacle problem, unless it was the case that lambda bar is special and gamma is special.
Indeed.
But you're ignoring that for the moment. You're ignoring that.
Yes.
And then the next theorem is you're going to send gamma to infinity and show that it converges.
No? Okay.
Another thing, an interesting question.
Yeah.
In equation 3, if we were to take the solution of the Moreau-Yasuda problem, then it would solve equation 3, provided ak plus 1 was defined with the correct y.
Yes. Of
Equals
course.
a k.
So you can see that it's consistent with the Moreau-Yasuda approximation, the iteration.
Okay.
In the sense that if yk plus 1 equals yk, then you have yk plus 1 equals yk equals y gamma, the solution of the Moreau-Yasuda.
Yes.
It's advancing one thing at a time, not the two things.
Okay, so now, despite the fact that this looks like a sort of active set procedure, which usually has a, I mean, if you think about it in finite dimensions, it could have a combinatorial connotation. Like in finite dimensions, you just get one component after the other right in your set in your vector y, and this could take a very long time. So this is why it's good to have a different perspective, and it turns out, and I'll soon give you some more details, that this is really a sort of generalized Newton step for this non-smooth equation, and you can show that this converges globally because of some monotonicity and locally at a superlinear rate. And this is a statement in function space here. So this is not upon discretization, so it converges at the locally superlinear rate in H01. Okay. So this is what you get. And of course, this is only true for every fixed gamma. And now we have to bring in the gamma loop. And the answer, and this is not a surprise, is well, if gamma goes to infinity, then we have a certain convergence towards the solution of the original problem. So this is a kind of standard step. Now we have two loops. For every fixed gamma, do this, and there are games we put there with lambda bar. And then on the outer side, we have to update gamma to do this convergence. And of course, if our gamma is far away from the limiting gamma, which means you have a very small choice, well, why solve this equation exactly? Why solve the Morishita problem exactly? You just do it inexactly and march on and update, and you would get some sort of good rule, and this is going to be part of the talk later on. Okay, so a few properties. Well, first of all, we have two cases. I call one case the infeasible case. This is when lambda bar is 0. And the answer is clear, why this is it's clear why this would be the infeasible case. If lambda bar is 0, and I may go back, and I solve the problem for a gamma, and I get a solution y gamma, which is less or equal to psi, well, then the constraint is redundant and I'm done. Okay. But on the other hand, if I have a non-redundant constraint and a gamma, and let's again assume lambda bar is 0, then you would always get the solution y gamma, which on a set of positive measure violates the inequality constraint. Okay, so this is why I call this the infeasible case. And there is and in the infeasible case we have a certain monotonicity, and this is why I said it globally converges. Because in the infeasible case where lambda bar is 0, because I have a y1, gamma 1 less equal gamma 2, and I get the relation between their corresponding solutions y gamma 1 and y gamma 2, and they're converging to the true solution from above. So this is of course because of properties of the operator. So there should be a monotone operator. Now, one benefit of bringing in the lambda bar is, as we just discussed, because if you would have a good estimate of lambda star, we should use it for lambda bar. Another benefit is the one here. If you choose lambda bar greater equal 0, which makes sense because it's a multiplier, and in such a way that it satisfies this relation, and this is, I think, something you see in the book by Kinderlehrer, Stambacchia, by Rodriguez and so on, so that you can get a feasible solution, even for the Morishita, well, they don't have Morishita regularizations there, but I think the idea is already in those books. So if you choose the lambda bar properly, what you get here is a feasible solution, y gamma, and also those solutions have a certain monotonicity with respect to gamma if you choose them correspondingly. Okay. So now the infeasible case converges from above, from the infeasible side. The feasible case converges from within, so to speak. And if this is, for instance, important for certain technological reasons, you may want to do the feasible case or otherwise the infeasible case. So it's a choice. Yes?
Why does it mean y star less or equal to psi?
Why?
Oh, the obstacle is 0.
Yeah.
No, the obstacle's not 0. The
No. So this one here?
Yes.
So the psi is the obstacle. So I have this constraint. Y should be less equal to psi.
Oh, sorry.
Okay. So y star less
Always
equal to
going
psi.
to the- Yeah, that's,
Okay.
that's fine.
All right.
Okay, so so this is.
But you have, in the feasible case, to get this monotonicity, you need this strong assumption.
Which, well, but is it strong? Now let's assume psi is a smooth obstacle.
Yeah.
I can evaluate the operator at psi, and let's assume the evaluation is so regular that I have a pointwise interpretation. Well, this is just data here. So this says if I choose lambda bar to be the pointwise max of f minus a applied to psi, then I satisfy this. So this is a sort of assumption which I can satisfy up front in a kind of cheap way if data is regular enough. But this kind of assumption is needed together with monotonicity of the operator to be able to prove
So you can construct upper and lower solutions
Yes, you could.
by iterating by both methods.
Yes.
That's an interesting, I mean, can be useful.
Indeed. Yeah.
But the other thing I think is that convergence rate with respect to gamma is quite bad, isn't it?
Convergence rate with respect to gamma.
Y star minus y gamma
Yeah.
in
Is-
H1 norm, for example,
should be
is the
something
square
like-
root of the reciprocal of gamma or something like that,
That's
which is very slow.
May I comment on something?
Yes, of course.
In problems in finance, especially this computing the values of options, usually these things appear. And then there is a theorem which says that the coincidence set is inside or contains, which one I don't remember exactly, the set when the obstacle is concave.
Uh-huh.
So let's say the A is
Yeah.
Laplacian, concave in the sense of operator.
I understand.
So it's Laplacian of psi is, in your case, I think is going to be positive because you're going from below. So that set is strongly related to the set
Mhm.
to the obstacles, coincidence set. I don't remember exactly which one is in which one,
Yeah,
but it's
yeah.
easy to see in 2 minutes.
Yeah.
And that already gives you very good information where to start.
That is true. I mean, we do have here, let's say we have a sort of simple information which says, if I look at this equation, which we had earlier with the lambda stars and the y stars, we know that lambda star has to be greater equal 0. So whenever f minus h psi is negative, well, we already know that this is not a
The
location
situation you want-
so where we can expect. So there is some a priori information. And I'm also sure if you bring in some further, well, properties of the operator and of the obstacle psi, like concavity, you might even further nail down the location of the active set. But the sort of simple distinction is already by signs of these data terms, and this would already allow you. And this is how we usually initialize the algorithm in a way that we try to.
I was
bring
thinking
this-
more like, once you have that set, that could be a set with boundary values. You can just ignore that set.
Okay, yeah.
The boundary values will be solved.
Mhm.
So you just need to track a very little set.
Possibly, yes.
Mm.
That's true. Yeah. Okay, and what we do then is we say, okay, we collect all these pairs, y gamma and lambda gamma, and say that this gamma now induces a path. It induces a primal dual path, primal because it includes y, and a dual path because it includes lambda. So I'm now interested in these paths because we should come up with a good idea of updating gamma next, because I've given you on the previous slide a local fast convergence result, and I told you that there is convergence if gamma goes to infinity. Now you may say, choose a very large gamma up front. Well, I can do this, but then I still have this convergence, but the radius of fast local convergence will be small. If I choose a very small gamma, that radius becomes large of fast local convergence, but on the other hand, I'm far away from the limiting problem. So I would like to find a sort of update regime, and this is why I'm next interested in what I call here the primal dual path, and very soon I will show you the so-called path value function. Yes?
It's important to distinguish between two types of convergence.
Yeah.
One is the convergence of the Newton iteration, which is like an iterative index going to infinity, and the other convergence is the convergence as this parameter gamma tends to infinity.
Yes.
So these two things, you might want to link those two.
But
When you took, I guess, for non-experts, I guess it's important to distinguish between the two.
yes.
Yeah.
Okay. Yeah, thanks for pointing this out, but this is indeed the case. So we have two iterations going on. The one is this one. This is what Charlie just said. It's the k iteration. So I'm sending k to infinity, and I get this locally fast convergence. But this is for a fixed gamma, and then I have to have a second convergence consideration, which brings gamma to infinity. And this is just a sort of crude result, which says if gamma goes to infinity, there is strong convergence. But of course, thinking algorithmically, I don't want to solve these problems exactly for a finite small gamma. And I cannot just take a very large gamma, because this doesn't tell us anything about how we should update gamma. If I take a very small gamma, well, I'm far away from the limiting problem. If I take a very large gamma, then the local convergence will be confined to smaller regions around the solution y gamma. So now I need to balance these two. And if you really want to, I can bring in a third convergence principle, which would be upon discretization. I discretize, I have a mesh width, and then you may say, well, if I have a discretization error, and I have an approximation error, and I have the error coming from this iteration, how can I balance all of these iterations so that I do as little as work as possible, but still approach the solution as quickly as possible? Okay, so now I'm now marching towards the second type of convergence. So we clarified in a quick way that there is a locally fast convergence. I'll come to this back later on, and now we would like to update gamma in a sort of meaningful way. For this, I introduced the primal dual path, which is defined like this. And well, the first observation is it's bounded. So regardless, so it has a sort of uniform bound, and this is what gives us this convergence result, which we have just seen earlier. So this is just the second statement of what I have had in the previous slide. Well, if lambda bar is 0, well, I have to make a distinction here. Obviously, if lambda bar is not 0, I only can get this boundedness if this r is positive. And it is very simple, and r is the range for my gamma. So gamma starts at little r and goes to possibly infinity in the limit. And I need to have r positive if lambda bar is not 0. And there's a very simple reason for this. If you think about this one, now if you have a lambda bar which is not 0, and this gamma can go to 0 in such a situation, this would blow up, and you can't get an estimate. But if lambda bar is 0, this doesn't happen, everything is fine. This is the reason for this distinction here. So if r is positive, well, if lambda bar is not 0, I have to take r positive, but could be arbitrarily small, and I have boundedness depending on r, and if lambda bar is 0, I can take r even equal to 0 and have boundedness in this range. I can even say a bit more, because I would like to learn how the solution and the multiplier estimates lambda gamma depend on this on this parameter gamma. And here it says we have a global Lipschitz property. Okay, so this path is globally Lipschitz with respect to gamma. This is already interesting because I'm now wondering if I update gamma, well, how does y change? Y gamma change? Does it jump? Is it smooth? Does it change a lot? And this is why I need to understand smoothness properties here, because this will also dictate later on the gamma update regime. Yeah.
Why do you keep y gamma and lambda gamma? Could you just keep lambda gamma or y gamma? Because if you have y gamma, you've got lambda gamma.
No,
if you've got lambda gamma, you've got y gamma.
I agree. This is what I said earlier. This step is sort of a convenience step. You don't need it really. I mean, we can focus on y only, solve the whole thing, and then ultimately, if you wonder what is lambda, you can just use such a step and get the lambda. But we don't need to. So this is just a sort of add-on. So there should have been maybe a line saying this is the core algorithm because it nowhere needs a lambda gamma. And I could also rewrite the whole thing probably in lambda, and then I could reconstruct the y afterwards. This is true. So, but for completeness, I carry both along. Okay, so now what's the difference? Well, how do we update my gamma? So we have a little bit of information already here, but if you have globally Lipschitz and consider this as a function from R into some Hilbert space H01, for instance, in the y part, well, there's a finite dimensional domain, so to speak, and we may think about differentiability or directional differentiability properties of this function y as a function of gamma. Okay, so I would like to know how it changes if I change gamma. Well, first of all, a little observation. If I look at what I call here the value functional, so this is the objective functional of the Morioshida regularized problem evaluated at the solution. Okay, this is the value functional, which is now only a function of gamma. Okay, then it has typically this behavior. So let's assume here is 0, and here we're marching towards infinity. Then in the feasible case, we're approaching the solution from above, as we have seen in the earlier theorem, which says we allow violations for smaller gammas, but obviously we are converging to the solution, which means these violations have to vanish. And this is what the value functional shows you. So somewhere here in the limit, you would have the optimal objective value for the original problem. And in the infeasible, this was the feasible case. And in the infeasible case, we have a smaller function value, because we allow violations. This is why we can have small objectives. There's a bigger range, so to speak. And we approach the optimal value from below. So in the feasible case from above, because we always have to stay feasible, but only in the limit we find the true objective. And in the infeasible case, we allow violations, so there's a bigger space for search for y. This is why the objective is smaller, but in the limit they both should approach the same value. Okay. This is the picture here. And the idea is now, well, since those, and this is not, I mean, this is one example here, but you could come up with different types of problems, and the value functions will more or less qualitatively always look like this. So there is, let's say, a sharp increase, and there is a certain curvature, and then it hits the asymptotic region here, the value function. So now the idea would be the following. The value functional maps a scalar onto a scalar. Now we would like, and it's a function of gamma, and we would like to, and it involves the y gamma, which we know already is Lipschitz continuous. Now we would like to take the value function to find a guideline to update gamma. So you are given a gamma L, say, and you would like to move to gamma L plus 1 by the value function.
Sorry, just a question on something you said. You said that this is typical of the way it always is going to be, essentially.
So this is kind of typical.
Yeah.
Yeah.
And so just a question about the curves then. So the feasible one seems to converge more quickly at first and then slower.
Yeah.
Is that included in your statement about it?
This is not included.
Okay.
So this is a good point. So I consider the conversion. So this is just one, say, arbitrary example.
Okay.
But I cannot claim. I have not looked at it whether this is, has any meaning or not. That this would be a general statement. I don't think it's general. Okay. So thanks for asking. Okay. So this would be now my guideline for updating. But how can we do this? Well, let's first study this this v function a bit further. It turns out that it's differentiable, this function. Well, first, I mean, there is a lot which I don't involve here, but what you can first do, now given the global Lipschitz property of y, you study differentiability properties of y. So you get the directional differentiabilities. So you sit at the gamma, you look to the left and to the right, and you get sensitivities. You even get the differentiability property under a certain non-degeneracy assumption, but I don't go into those details. I'm primarily interested in the value function. I can differentiate the value function, and I get the derivative which looks like this. Okay. So this is already the general case, and it's true in both situations, the feasible and the infeasible one. Now for the infeasible one, the lambda bar is equal to 0. Well, obviously this boils down to just this term here. And this first observation is the term is always non-negative. Now let's go back to my picture. In the infeasible case, which is the blue line, the derivatives of the value function are always positive. So this is just something which you immediately get. And the other information which is quite nice, it has an interesting simple structure. So you fix gamma, you solve the problem, and you can get y dot almost for free. You just need to evaluate an integral at the solution. So this is almost for free. And we can also say that y dot is always positive unless y gamma is feasible. But if y gamma is feasible for a finite gamma, we have already found out, and then the constraint is redundant, and we are released from updating gamma because the y gamma is the solution y star, and we can stop. So which means we always have y gamma positive unless we're done. And for the lambda bar as chosen before, with these data-dependent conditions, we have feasibility, as we already know, and we have that y dot is less equal, so this can be again extracted from this, if you go through it. And again, of course, it matches what you see here. In the feasible case, the derivatives are always negative. Okay? And this is reflected. Okay. And in both cases, as we've just discussed, y dot 0 implies that we are done. We don't need to update that.
V dot.
V dot, okay.
We'd like to know y dot, but we can't have it.
Yeah. Well, actually, you can have it, but only at the expense of solving a sensitivity equation. So you will need to solve another PDE to get y dot, but then, and this brings me now to this observation. I think this was just Freud, which played his game. We have v dot characterized without y dot. Obviously, there is nowhere a y dot inside, so we do not need to go to these sensitivity equations, which would be quite expensive because we need to solve a PDE to update the scalar. Sometimes you need to go to such an effort, but in this case we don't. And this is also a rather general principle that value functions with respect to parameters have derivatives which, under certain assumptions, do not depend on those parameters. On the sensitivities of the solutions with respect to those parameters. So this is what we see here. There are some further observations, but maybe I don't go through these details here. So you can do, for instance, the following. You can estimate the difference between y gamma and y star. As we've just said, there's the general capital O of 1 over square root of gamma. But you can also estimate it in terms of the value function at the true solution. This is v star. So it would be sending gamma to infinity. And what you see here is a kind of linearization of the value function at gamma in a certain direction. So you somehow have an upper bound, and there is again the coercivity constant of this bilinear form. You have an upper bound which depends on how well the linearization approximates the limiting value. Okay, and there are some other observations which, for instance, allow us even to characterize the second derivative. But now we need to know the y dot, which is the sensitivity of y with respect to gamma. So there are such observations, and we can even somehow trace the sign of the second derivative, and it all is completely in correspondence with the picture which I've given you earlier, that one has a negative curvature and the other one has a positive curvature.
So, all right, so V gamma is computable.
V gamma is computable once you have, let's say, solution, approximate solution. Now you need the solution.
V dot gamma is computable.
V dot gamma is computable because it just involves
V dot
this,
gamma is
yeah.
computable.
V double dot
But V
is
star
expensive.
V star is unknown, so
Okay.
doesn't give you at the moment doesn't give you any a posteriori information, does it?
No. Okay, and you can do the same thing for the infeasible cases, just the second derivative looks a bit more complicated. Okay? I think I don't go through the details here. So the idea is just we need to find an update rule, so do analysis on the dependence of the various quantities with respect to this parameter, and use the value function as a guideline later on. So now what are we going to do? So we have these observations. Y dot is non-negative. Y double dot is, well, there's non-negative, Y double dot is non-positive in the infeasible case. The reverse signs for the feasible case. And now you may say, well, I could come up with model functions mimicking such a behavior. And again, I'm short here. So this is looks like arbitrary choice. But now I have a model function n gamma, which should replace my v gamma, because after all, v gamma is expensive. Maybe. And if I would like to update, I need to have more information on v as I march along than I would like to compute by solving PDEs. So I would like to come up with models. Now this model here with constants C1, C2, and E, I mean, don't ask me why E, but there is a reason for that which is unexplainable, I think. And a certain initial condition, so to speak, with respect to gamma. This would be the unconstrained problem. There is no penalization involved. You completely ignore the constraint. You just solve Poisson's equation and evaluate the objective. You get this n0. So now you can with these conditions transferred to the model function, you can now fix the constants C1, C2, and E, and you get the model. So you are given a gamma. You have an initial condition. You need to fix 3 parameters. So you need to find 3 conditions and you fix them. So this looks kind of arbitrary and simple, but I could even have given you a probably more impressive reason by writing down an ODE, which comes out of the PDE and would have a solution of this type. So there's a relation by simplifying the PDE and coming up with solutions, and there would be this sort of rational.
So you mean that M is a model for V?
M model is a model for V. So M at 0 is equal V at 0, and I would like to have a similar qualitative behavior, and I need to fix the constants by sort of interpolation.
Basically, you're saying that if you choose C1 and C2 in the way that you just under those conditions, then M dot and V is greater or equal to 0, and M double dot is less or equal to 0.
Yeah.
So would you mind writing down the ODE that you get?
I'm not so sure whether I have it in my mind. So we can talk about
If I can
it.
maybe ask you about that.
Well, you just differentiate.
Well, you could differentiate this one and get around it. Okay.
M dot is equal to C2 equals gamma squared.
Now it was a bit more tricky. So
Which one you could,
Yeah.
which means that since E plus gamma is related to
No, well,
M in that way,
I'm happy
you
to
can-
write it down
You can
afterwards,
always
but
do it
it's,
anyway.
it comes essentially by just replacing the Laplacian by double dots in a sense, and so on. Okay, so it's not just the first order type.
No, no, you can.
Okay, and a similar consideration now for the feasible case, but I think I don't go into the details here. So same idea, preserve the structure with certain conditions which ultimately fix the constants. Okay, now what we do next is, now we have a model for V and we need to update. Now how do we update? I think I can't give you all the details, but let me first explain. Well, I could be very strict and say, give me gamma, I really solve the problem after discretization down to a very accurate solution. But this probably is too expensive, in particular if gamma is far away from its limit in a sense, it's still small.
I just go back to the previous slide again.
Of course, yeah.
Gamma tends to infinity.
Mm-hmm.
Then we know that that's what we want
Yes,
for V.
that's what
So already you, in some sense, have the equilibrium. You have the final energy encoded in those constants.
I do, but I don't know, of course, the
No,
final
you
energy.
don't know it exactly.
So-
So you don't know what these constants.
So obviously the C1 in this case will turn out to be the V star in the limit.
Yeah.
But as I march along, I don't have that information, so I have to certainly find certain conditions which ultimately give me those solutions. Yeah.
But it seems to be some kind of miracle going on because you're modeling V of gamma,
Yeah.
but it's not V star that you want compute. So you might very well be able to choose. You might be able to
Yeah.
model. So it's really Y star that you want.
Yeah.
And so at the moment, if you can imagine having a model like this will allow you to sort of use the information that you've got to predict what V star might be, and therefore choose an appropriate step length gamma.
Yeah, but that is true. But this is probably, I mean, the optimistic approach. Say it like this, because if I'm sitting somewhere here, I mean, of course, I would like to know how the Y star looks like further down here. But if I would like, I know if I do a very huge step in gamma, then I'll compute that value, but at the expense of many iterations.
Yeah.
So what I'm interested in is I'm sitting here.
Yeah.
I just need to understand the neighborhood of this point reasonably well, because this will tell me whether I have a sharp curvature, because sharp curvature means lots of change in
Yes.
and so on. Then be careful with updating gamma. If you sit somewhere here, where you may say
Yes.
not many changes, large updates. So somehow I'm interested, of course, in Y star, interested in V star, but if I'm somewhere in early along the iteration in gamma, I should not be too optimistic. I should rather understand my neighborhood, and this is what these models try to do. Okay, now, as I said, maybe early along gamma we do not want to solve exactly, so let's solve inexactly. How can this be done? Well, we define residuals. I think there's no big surprise. In the regular case, if you have a less regular case, you have to take different norms here. You have here the first equation here of the complementarity residual. This is where we take the lambda gamma as an approximation of the lambda star. You define a neighborhood. You say, well, given some constant beta, and here this is where we see the skirt of gamma, as we just discussed earlier, emerging. You say, I'm happy if my solution y gamma, approximation, let's say, of the solution y gamma lambda gamma falls into this neighborhood here with respect to residual. So this doesn't mean I need to solve it exactly. Okay, so this is just a picture, I guess, for the infeasible case. You start somewhere here, you're happy if you come into that neighborhood, and then you march on as you, and this neighborhood is shrinking as gamma increases. So which means early along you allow huge approximation errors in the solution, but as gamma increases, your neighborhood becomes smaller and smaller. And this is somehow sort of a picture one could have in mind.
So you mean by that, if that circle, in that picture, if that circle is large, it means that you're allowing K to be smaller.
Yes, I stopped.
in
the
effect.
error.
I mean,
Yes.
you're allowing the error in the stopping the Newton iteration
Yeah.
to be possibly larger, but as the further you
Yes.
go along with gamma, then you're shrinking
Yes.
that circle, so you want better convergence for your Newton iteration.
So let's say the optimal choice would be you fix a gamma, you do one Newton step. You're in a very big circle probably if gamma is small. But you hope that one iteration is good enough to bring you into that circle. Because it can't be too large. Because if it's too large, then you're too far away from your true solution. And then all your models and everything are just of very poor quality. So this circle somehow should not be too large. And this is an issue what too large means, because it's kind of complicated analysis, which is not involved here. But then ideally you would like to do one Newton step, get an approximation for y gamma, an approximation for v gamma, a new model parameter, and you do the next gamma. And then you hope again that one Newton step is enough. This would be the ideal picture. And this is what this algorithm does. You start with a gamma, you find an approximate solution, in that neighborhood you update gamma according to some rule, and then you reiterate. Okay. and actually, in order to achieve this, you would apply the Newton step, which I've shown you earlier. Now, well, how do we update gamma? Maybe I should not even go into the details here, because there's a sort of sophistication on how to update gamma, and what it does, it balances a feasibility measure, so this is a sort of feasibility violation, with a complementarity measure. So there's the inactive set, y should be less than psi. On the active set, y should be equal to psi, but if in an infeasible case, for instance, y would be larger or smaller, and depending, could even violate, I should say, depending on this, I'm measuring here complementarity. Now I balance those measures plus some other terms here, and this gives me now an update rule for gamma. And I introduce safeguards based on the model function. Now what would be such a safeguard? Now if I go back to the picture, you would do the following. You would say, well, if I sit here and I compute my linearization, we have seen that linearizations are also useful upper bounds. Would I have the true information? So if I compute the linearization, but it turns out that there's lots of curvature, I very soon will be far away from the true function value. So if it turns out that I'm getting too far away from my approximate value v gamma with my linearization according to my model, then I stop the update for gamma because I'm getting too greedy in a sense and too far off the track. And this is what the safeguard with respect to the model function indicates here. So that we use a linearization of the model function and check how far the linearization evaluated at the candidate gamma for the next larger gamma is away from the corresponding values. And if that's too large, then we just take a small gamma. Okay, if you do this, you'll get the last line here. What you see here is one particular example. I don't give you the data here, so it's not trivial. It has an active set, it's not redundant, but what you see here is we do a mesh size, so we discretize. It's very coarse, so I mean, I'm not going to verify meshes obviously here. So this is the mesh size of a two-dimensional example in each direction of a uniform mesh. And as we go along these columns here, we refine the meshes obviously. What we see here is that the number of iterations are kind of stable with respect to mesh refinements. We have 7, 9, 9, 7, 8, so there's a sort of mesh independence going on here. I mean, there are some parameter adjustments which could explain variations. What you see in parentheses is the number of Newton steps we need in order to get into these neighborhoods for each gamma. So you can see that we need less than 2 Newton steps in average to get into this neighborhood n. So you have a gamma, you do at most 2 Newton steps, then you're fine enough, and you update gamma again, and this is what you get. You may do different solvers. So this PDAS would be now a semi-smooth, a finite dimensional semi-smooth Newton solver without this platforming. So you just say, I discretize, there are very good finite dimensional solvers, semi-smooth Newton in finite dimensions. I apply it. I always start from the same point, so which means you have this, an initial point, take it to be 0, which is exactly discretized on all meshes. You always start from 0. On a coarse mesh, you need 14 iterations. On the next finite 27, then 54, then 113, and 226, and so on. So you can see how the number of iteration grows, and this is a typical mesh-dependent behavior. I mean, of course, the experts in multiple would say, but at least a very quick fix is to do a nested iteration, which means go from a fine to from coarse to fine meshes and use always prolongations as initial points. I agree this should be done, but this was not done here just to show you how the classical finite dimensional solvers without PDE numeric techniques would exhibit mesh-dependent convergence. In the middle, you see an interior point type method, which is another way of following a path in the interior of the set, and I don't go into the details, but again, it's a path following method, and because it's a path following method, it's much more simple, but still needs more iterations. Okay. This is a sort of first assessment, and now you can do the same thing. So this was for a little model problem, and then we did the same thing for Cahn-Hilliard. I think many of you have seen the slides, so I can be very quick. So Cahn-Hilliard, we know, is a method, or is a model for phase separation phenomena put into mathematics in a sense. It uses a phase field or order variable u, which is -1 if you hit a pure phase A, it's +1 if you hit the pure phase B, and it's somewhere in between if you have a mixture. Okay? So this is how you would usually view it. Then we know that the equation arises from minimizing the Ginzburg-Lambda free energy. We have a diffusive part, we have this entropy mixing part psi here. There's a volume preservation, and of course we know that this psi here then is important. There are many choices, and if you do the obstacle choice, which I have shown you here, which means you have a concave part if you're in the mixed phase, this concave part pushes you to the pure phases, and otherwise you're immediately penalized by infinity. This is what this psi does here. But you get the variational inequality of the first kind, and you can well, rephrase it as a system like this. So you have, first of all, for the chemical potential W, this equation here, whereas here you see the indicator function of this set K, which is -1 and 1 here, so your function here should be between the bounds. And you have the sort of margin peak or gradient flow down there. And of course, we have additional boundary and initial conditions, which I believe will. Okay, you can write down, well, and what you do next is you do a semi-discretization. I think you have to see at some point we should stop. We have if you do a semi-discretization of step width tau uniform in time, then you can rephrase every step of this time dependent as an step of this time dependent. Again, notice this is a variational inequality here written as a generalized equation by using this set valued operator here. But again, I could have written it as a variational inequality of the first kind. So this would be a variational inequality of the first kind, and this is a gradient descent scheme which is attached to it. If you do a discretization in time, then you know that every time instance solves an elliptic PDE constraint optimization problem, which can be written as a variation inequality of the first kind. And if you apply the method, then you can come up. Okay, it seems that it moves. So there's a move, and you can do the same thing here. So there's the gamma parameter, which was moved up to 10 to the 7. So so this is a kind of nicely behaved problem, because in the first couple of, I mean, if we go back, in the first time instances, a lot of change occurs in the active regions. Now you have the active regions would be red and blue, and this would be the inactive region in between. So there's a benefit probably, like as you mentioned, because ultimately I could think about confining everything just to computing the PDEs on, well, not in this context, okay, forget this comment. But there's just a little motion here of the boundary. So we have a very stable active set as we march down the time history, which means we always have very good initial guesses for Newton's method, and the path following can start with very large guesses for gamma, because your initial guess is already quite good coming from the previous time step. So each time step problem is one of the problems we have seen before with these iterations, and if you move from one time slice to the next time slice, you use the previous solution as an initial guess, and this is usually a very good one.
So
okay,
in this picture, people might not have observed it, that for the obstacle problem, the red is a coincidence set.
Yes.
The blue is the coincidence set, and that very yellowy, is it yellow? Whatever color it is, green on green, yeah, is. No, it's the. It's more. It's where the obstacle is.
It's the inactive set. So
it's where the equation, where the elliptic equation goes. the second order elliptic equation holds.
I mean,
So just,
yeah.
that's so the free, so it's has its own particular.
You mean the
Yeah.
equation on the free boundary?
No. So the red region is a coincidence set.
I think
The
that's
blue
what you-
region
yeah.
is a coincidence set. The region in between is actually is it's a thick region. It's a thick region. It's got two free and the free, and so that's where the second order elliptic equation holds. Yeah. Otherwise, it's obstacle.
And I mean, there are many specialities here, and I think I could continue because you may say, since the region is small and somehow behaves predictably, you may even come up with more tailored solution schemes than the one that I showed you earlier, because you may really take into account that all you need to do is solve in a neighborhood of that region as you march along time. So there are other types of solvers available, but I just want to point out that the scheme which we've seen before can be applied here quite successfully. And if you have a time margin, then you can benefit from the fact that as the evolution is down the line, in a sense, you have little changes in this particular example in the active sets and the good initial cases, and you should bring all of that information into your iteration. Okay, I think this is a point probably to stop, because the next step would be variational inequalities of the second kind. And I have more material, so let's see how far we can get in the afternoon. At least I think this would be the second type of problem which we need to discuss probably, and then there would be other things, because for instance here you have seen that there is a sort of adaptive mesh going on. This would also be part of numerical solutions, and I could take a little bit on how to come up with estimates for these adaptive refinements of the meshes here. And time permitting, I could also quickly explain a few aspects on quasi-variational inequalities, which look somewhat similar, but are indeed more complicated and much nastier. Okay, with this I would like to thank you for the pre-lunch session, and we will see each other next week.
Any questions? More questions?
I want to ask.
You're going to ask in more detail. Okay, so maybe you will. It's okay?
Well, I just wanted to.
Yes,
yeah.
Can I see now, or would you like to do that
I
after?
can.
Or what?
I can find